Welcome, my name is Mark Upston, Senior Director of Product Management at Bentley Systems. Today I'm going to discuss how Bentley delivers big efficiency gains using a digital twin platform to reduce the cost of energy for offshore wind projects across the whole lifecycle supply chain. So let's get started. So Bentley's portfolio can deliver in three key areas. Firstly, planning and designing in the most cost-efficient fixed and floating foundations. Secondly, reducing construction schedules, which also relates to installation costs and improving construction management, and all the way through to tow-out and lifting simulations. And thirdly, providing remote operational monitoring, inspection, and predictive maintenance services. So let's hear what is a digital twin.
A digital twin is a digital representation of a physical asset, process, or system, as well as the engineering information that allows us to understand it, model it, and get its performance. Typically, digital twins can be synchronized from multiple sources, including sensors and continuous surveying, to represent its near real-time status. This synchronized data can be used to gain valuable insights, to more fully understand the physical asset. Infrastructure digital twins, or iTwins, are emerging now because of a convergence of technologies that enable an immersive and holistic view of infrastructure. Now, these include 3D and 4D visualization, reality modeling, mixed reality, and geotechnical engineering. Bentley's goal is to enable a digital twin ecosystem that will improve our understanding and transform the performance of the world's infrastructure.
And a digital twin for offshore wind farms should be comprehensive across the whole complete life cycle, as I mentioned, from planning to design to engineering analysis to construction simulation through to operations and maintenance, and even with asset performance and maintenance. So let's look at the planning phase. Let's look at a unique tool called Field App and Field Twin from Bentley's partner Futuron. As an offshore wind planner, they typically want to combine the meta-ocean data with the seabed depth profiles, the geotechnical soil conditions, and the various turbine equipment options. So different wind farm layouts can quickly compute suitable foundation sizes and project costs. And when the project moves from detailed planning, procurement, and construction phase, the field twin data can be connected to the Bentley iTwin platform. So let's look at this in action. Futuron's Field Twin Platform as a Service provides engineering and field staff a way to aggregate and visualize all the data critical to offshore wind projects. The proposed layouts can automatically be generated within the 3D model of the seabed depth profile for a clearer visual evaluation by developers and stakeholders. It is easy to design and compare various substation, turbine configurations, and cable routing, and the costs associated with each configuration, including accounting for existing assets like oil and gas drilling platforms which may be in the area. So next is design. So how can we lower your design cost? Well, Zentech Engineering from South Korea designed this offshore wind turbine substructure. Bentley Offshore design approach enabled the project team to reduce the structural weight while maintaining sufficient structural capacity and strength given the wind and wave loading on it. The construction of the optimal design took 20% less time with Bentley's SACS application. And these high-performance computing options are available like cloud computing, and they allow for large-scale analysis. So you can explore many more design alternatives and produce a more optimal design. And similarly, we have another high-performance platform using a local area network grid. So let's take a look at some simulations here. We can produce some very complex loadings like on a fixed foundation jacket or monopile like you see here in a single software product. Or even on a floating platform structure with the turbine loads on it, you can see as it's floating in the waves. And even a complex multi-body lifting operation from this barge in a floating semi-submersible here can be simulated. So we can integrate coupled and uncoupled aeroelastic analyses and that captures the turbine vibration with the structure and the motion behavior of the fixed or the floating platform to deliver an accurate simulation under even extreme environmental conditions. But so who are the key wind turbine manufacturers in the offshore business? Well, you can recognize Siemens and MHI Vestas, but we also integrate with GL Bladed, Fast from Enroll, and we even have an uncoupled turbine process as well. We have two products. The first is Open Wind Power Fixed Foundation. It's been around for about 8 years now, and it can analyze and design jackets and monopiles to support those offshore wind turbines. And the second is a Open Wind Power floating platform you'll hear from shortly from Dr. Daniel Veen. And that was introduced end of last year. It's a single product to design end-to-end the floating platform, support those dynamic loadings that you just saw in the earlier animation. Thanks to Open Wind Power, Keystone Engineering out of Louisiana, they were able to adapt a deep water jacket structure from the oil industry and significantly reduce the amount of steel required. And it resulted actually in an installed cost savings of 20% on the 30 megawatt Block Island project, which is near New York. They also shortened the design cycle by 50% compared to typical European offshore wind projects. We also are able to handle and manage thousands of load simulations that can be generated in minutes, and we can manage those in Microsoft Excel. Parametric modeling is a big time saver, and particularly modeling jacket structures. Companies like Hyundai Heavy Industry and PowerChina are able to reduce their design time by 20 to 30%. And even batch operations to complete multiple iterations of design and analysis to find the most optimal design solution. So let's take a look at a similar example in our floating platform, Open Wind Power Floating. Here we see a parametric modeling using Excel, and just entering a few dimensional parameters, we can very quickly change and generate a full parametric model in seconds, and for the full semi-submersible cylindrical platform. For design review collaboration, we have a solution on the cloud using Bentley's iTwin that you saw earlier, and you're able to launch a design review session from inside the software, and any team member can be invited. Offline sessions are also available, and they're available to review, mark up, and share with the whole engineering team or even contractors. One similar project that we had in China, which is a digital twin project, which is in the Three Gorges region in China, designed by Shanghai Investigation Design and Research Institute. And this is China's very first anti-ice flow offshore wind project. It used special monopile foundations, and they modeled a detailed 3D substation model that you can see here, and using all the multiple simulation and design tools that we have, and they're able to achieve a single intelligent digital twin model. So the design collaboration I just mentioned, where you can launch a session from inside the product, like in Saxia, invite any team member to it, and the iTwin design review service launches in the cloud and on a browser, and you can, with all those team members invited, and you can review, mark up design issues, and even come back to them later. There's a complete design history as well. About 2/3 of all offshore wind farms use monopiles. So what if you could reduce the size and weight, and therefore the cost and maintenance on these monopiles? And also, what if you could have greater confidence in using suction bucket foundations, which can provide big advantages of reuse, they're marine friendly, and they're also big savings on total capital cost as well, even up to 40%. So companies like Siemens Gamesa, for example, have been investigating mono buckets, and certainly a number of China and Korean companies have started to use more suction bucket designs on jackets to achieve $1 million in savings. And here you see a new suction pile design workflow that we're just about to release, where the complete SACS structural model is integrated back into Plaxis 3D, and a detailed finite element soil analysis is performed, which includes the interaction between the multiple suction piles, and then the whole soil characteristic is updated in SACS, and the final structural analysis from fatigue design can be completed. Of course, like I mentioned about the monopiles are getting larger and larger, up to 15 meters in diameter and 100 meters long, and to be designed in deeper waters like up to 60 meters in depth. But very conservative design methods are still currently used, which result in very heavy, expensive monopiles that weigh up to 2,000 metric tons. So any solution to safely design monopiles and remove this conservatism is a win-win for the owner and the supply chain. So here in this video here, we see the new SACS Plaxis monopile designer integration, where you can analyze the geotechnical behavior of your foundation for your monopile, either in a full 3D numerical approach or using a rule-based PISA design method in Plaxis monopile designer. The soil response curves obtained from this geotechnical analysis can then be automatically converted and read into SACS, and you can remove that conservatism I just talked about of up to 35% saving in installed cost. So construction is another way where we can help you remove save cost and remove conservatism as well. So Synchro 4D has a resource management optimized scheduling to accelerate construction. Here you see in a onshore wind farm where they're erecting an onshore wind turbine and simulating that, and doing all the resource management, the time simulation to do that lift, and scheduling the whole process as well. And this reduces non-conformances and big gains in risk mitigation. And we can also do a similar complex simulation in transportation and lift, similar to what I showed earlier as well. So operations and maintenance, we have a new partnership with Microsoft and Doosan Heavy Industries. Here you see a project in South Korea. A 3D reality model was generated for the project using Bentley's context capture. And out to the offshore here, you see the turbines, and the live power from any of these wind turbines can be viewed from IoT sensors linked together. The observed power, the design power can be seen in real time or across any time period. And the power and any component warnings can be displayed, and with the weather forecast data and AI, the digital twin can predict the power production. And like I mentioned, we can generate any high definition 3D reality model using photogrammetry, drone flyover with high resolution photos. There is our real-time asset monitoring, so we can monitor with that sensor data to track turbine blade erosion performance, gearbox vibration, or platform corrosion and movement, all integrated into one digital twin model to give real-time historical reports. And then lastly, as I mentioned, operational costs can run up to 40% of the total cost of the offshore wind farm. So using some structural and mechanical integrity management, we can reduce the maintenance cost and extend the life of the turbine and platform as well. So those three areas, designing, construction, and operations and maintenance. Lastly, I just want to highlight a couple of projects here. Here's the Three Gorges project I just mentioned, with up to 70% efficiency gains, and they saved a combined 600 man days on the project. Here's a project in the Netherlands where the use of Moses was used to reduce the amount of steel on the platform. The London Array in 2013 was designed by SACS by a company called Cowie. And an asset management project in the Netherlands predicts that using asset management can be a total cost saving of 4.3 million over a 20-year lifetime. So I'm going to hand it over to my colleague, Dr. Daniel Veen, now to show you the advanced modeling and design of floating offshore platforms.
Thanks, Mark. The Open Wind Power Floating Platform workflow comprises 6 elements: modeling, hydrodynamic analysis, aeroelastic analysis, time domain analysis, and structural code checking. The Moses modeler generates 3-dimensional hydrodynamic and structural models of floating platforms. Using the inbuilt meshing tools, I can easily create a tri-mesh to define the hydrodynamic surfaces of the deep sea wind floating platform. I can then define the linking structural beams directly through a dedicated Moses objects window. I can also import geometry from a range of file formats. Here I am importing a polymesh of a 5 megawatt turbine and tower for illustrative purposes. Once complete, this model can be saved in the native Moses format, ready for export to the Moses solver. I'll now import the model into the Moses executive. Here I've created a command input file that controls the Moses analysis. The model is ready to run, so I'll move to the ribbon and select the Run button to begin processing. Moses will locate the model in the desired location, compute its weight at this position, and then perform an equilibrium calculation to ensure the net forces on the body are 0. Moses will then compute the hydrodynamic database of the floating platform. It takes approximately 7 seconds to compute the hydrodynamics for each defined wave period, so I'll move to the next phase of the analysis for brevity. Here I'll compute the RAOs and then make use of the emit WAMET command to export the hydrodynamic data in the WAMET file format. This data can then be used by any aeroelastic solver that is capable of reading WAMET format files. I can view the results graphically by moving to the results layout. On the right hand side is the model created using Modeler. I can display the wave pressure at any heading and frequency combination. I can also plot any data created during the analysis. For example, I plotted the added mass and damping of the deep sea wind floating platform here. The WAMET format results, exported by Moses, can be read by third-party aeroelastic solvers such as DNVGL's Bladed. Here, Bladed is used to compute a power production analysis. The loads computed on the wind turbine are combined with the hydrodynamic forces to determine the trajectory of the body. These trajectories can then be exported along with the forces at key points, mooring, tower, for example, and the components that govern the wave environment, ready for inclusion in a Moses time domain analysis. I can also review the results of the power production analysis in graphical form and determine the overall performance of the wind turbine. Back in Moses, I have created a separate command input file for the time domain analysis. This analysis still references the same deep sea wind model as used in the export phase. Here I have 2 options. First, I can run a single analysis by referencing a specific bladed simulation. I can define the location of the bladed results in C-state folders and the Moses nodes at which to apply mooring and tower forces. Alternatively, if I have completed a number of bladed simulations, I can use the import bladed job creator to create multiple Moses command input files automatically. Moses will find all bladed runs in a given folder and create a command input file for each run based on the active Moses template. In the ribbon, I have a choice of running a single file, running all files sequentially in a batch, or running all files concurrently via a distributed network grid. This will use all available cores on my machine and any available cores on the local area network. Bladed can create thousands of simulations, so the grid analysis service reduces error and offers a significant time saving. For this example, I only want to run a single analysis, so I'll just click the Run button. Moses will begin to process the log file. The results from Bladed are imported, converted to Moses format, and then the time domain analysis begins. This simulation will build on the trajectories and forces from Bladed by including sea pressures and inertial loading. When the analysis is complete, I can move to the results layout to review the final data. On the right is the deep sea wind floater in the wave environment. On the left are results for wave elevation, the blue curve, and the exposition of the body origin in global coordinates, the purple curve. Using the built-in data handling tools, it is very easy to compare these results with those produced by Bladed. At the conclusion of the time domain analysis, the calculated loads can be used to perform a structural analysis in Moses. The produced structural data is saved to a common solution file for code checking using SACS via an API SDK. The SACS post and fatigue modules can be run automatically and the results viewed graphically in PostView. Here I have the structural model of the deep sea wind floater. I can view the stresses on both beams and plates and check against a wide variety of codes. If any of the structure fails the code check, the structure can be redesigned and the entire workflow repeated. That completes the Open Wind Power Floating Platform workflow demonstration.